Um, Hi, everyone. Thank you for the introduction. So today is the second lecture of this roundabout course. And today we will be just doing a quick recap of commonly used terms and definitions, as well as concepts that we use for in XR. And in particular, this will be about technology aspects. So now I would like to move forward. Yes. So here's our outline. It has only two main points. First, some definitions, and then we will talk about the technology, in particular displays, scene augmentations, localization, and interaction. Sorry. Better? So what do we understand under VR and AR? If you think about VR, this is an example we see here from the game Job Simulator. It is a completely 3D rendered environment. We can interact with all the different elements in there. So if you take a cup, you can throw it around, you can push the buttons. And so the user, because the environment is reacting to the user is feeling a sense of presence in this environment. Now, if we go from virtual reality to augmented reality, what would be the main aspects that change? Well, here is an example of what the same scene would look like in augmented reality. In particular, now we see only the computer screen is there, which is a computer-generated object. And it appears in my kitchen, in this case, on the table. And everything else is real. So the computer graphics are now embedded into the real environment. So they need to be spatially aligned in the sense of, if I walk around this kitchen table, the graphics are still remaining on the table where they have been before. So we create an impression that the computer graphics and the real world are one single environment. And we can see this definition has been the same throughout the years. So here is an opinion by Mark Bolas that AR brings reality back to virtual reality. And also here is the definition according to IEEE, that augmented reality is a concept of technology delivering a computer-mediated reality that enhances physical reality with virtual reality, creating the user's experience of just one reality. So there are many different realities that are being fused here into one, but if we boil it down to the main point, it's actually just two main things. We have virtual content and we have the real world, and they are being fused together so that the user can no longer distinguish between them and now is experiencing both of them as one combination. On the grade from the real world, where we have no graphics to the virtual environment that you have seen before, where there are only computer graphics all around us, there are, of course, different degrees. And this has been defined as the real reality virtuality continuum by Milgram and Milgram and Kishino in '94. So on the left here, you see just an image. There's this is a meeting room. There are no virtual objects.
I thought you meant like
and on the other hand, on the right hand side, we have just a completely virtual environment. So there's nothing real anymore. In between, you can see different degrees of a mixture between the real world and the virtual world. On the very left, you see again the same example we saw before, with just the computer screen embedded into my kitchen. And this is, so there's very little virtual content that is being added to the real world, and we refer to this as augmented reality. Now, on the other hand, you can see the same scene, but now the virtual hands have disappeared, and you can see my real hand being rendered in the same image. So here we see a little bit of the real world being brought into the virtual world, and this is then augmented virtuality. In recent years, the whole spectrum between that is on this continuum, except for real environment, has been also referred to as extended reality, or as Rob has defined on Tuesday, exciting reality. And when we create XR experiences, we are trying to achieve three goals, actually two main goals, immersion and presence. But I also have now listed here telepresence, because these terms have often been mixed and used interchangeably, but they mean actually very different things. I'm going to give you just a couple seconds. Try to think what these terms would mean for each of you if you heard them for the first time. Okay, I hope you all have an idea now. Let's talk about them in more detail. And why is immersion and presence important? You can see on the right-hand side on the slide, this is an image from treating patients who are suffering from very, very severe burns. So these patients, they're usually in a lot of pain whenever they are undergoing the treatment. And by immersing them into a virtual environment, you can distract them so much from the pain that they're feeling like they're in a different environment altogether. And if we can achieve this, is this now immersion or is it presence? Well, in this case, I would say it is immersion, because immersion is defined as the extent to which the computer displays are capable of delivering an inclusive, extensive surrounding and vivid illusion of reality to the senses of a human participant. It can also be defined as the psychological state that is characterized by perceiving oneself to be enveloped by, included in, and interacting with an environment that provides a continuous stream of stimuli and experiences. Again, here we see that immersion is primarily addressing the senses of the user. It is not about making the user believe that he's in a different location or in a different space. It's about providing believable sensory feedback through sound, taste, smell, touch, or visual, that the user is believing that what is providing is real. For example, if I touch a virtual table, I should be feeling some feedback from this table. On the other hand, presence is defined as a subjective sense of being in a virtual environment. Importantly, the sense of presence can be separated from the ability of a technology to immerse a user. And as such, presence can be defined on many different aspects. We have spatial presence, where it is about the user believing that he is in this virtual space. Social presence, it is all about believing that that the characters in this virtual space are behaving realistically. Imagine you are in a room and there are realistically rendered figures around you, but none of them are moving, none of them are breathing. It feels surreal, and we will never believe that this is actually real. There are other aspects such as co-presence, the feeling of being in the same environment with somebody else. Involvement and realism of this rendered scene are other aspects. Now, as the last point, I want to define telepresence. Telepresence originally came from remote work. So it was defined by Aiken in 1983 as the manipulator have the dexterity to allow the operator to perform normal human functions, and the operator receives sufficient quantity and quality of sensory feedback to provide a feeling of actual presence at the worksite. So here it is not about communication with other people. It is about, imagine you're controlling a robot, and now you are provided feedback from the worksite, and you are performing some operations that allow you to operate this robot in real time, and feeling like you're really operating this robot in front of you. But nowadays, telepresence has been also become more commonly used in telecommunication. So the feeling of presence with somebody else, co-presence in this case, that we are sharing the same space and that we are potentially teleported to the other location. So we are in the same location now at a different place. But it doesn't have to be very high fidelity, super realistic rendering like you see on the left. So we can see that there's a 3D model that is being transported from one location to another. And you could say we are feeling a sense of co-presence and spatial presence. In one sense, telepresence for this particular interaction. But if you look on the right, well, it is, I think Holger showed this video on Tuesday. You have just two images of two people looking at the same scene at the same time. And because they can see what part of this panorama the other person is viewing, they are creating a feeling of telepresence, that they are sharing the same space and that they are communicating. Technically, I could be seeing your reactions right now to my talk through Zoom. And this could be seen as a sense of telepresence as well. Now, to create this sense of immersion and presence, we can utilize a lot of technology, and many technological aspects are playing into this. Here are the four main ones. These are sense augmentation. So what information do we provide to the senses of a user? Display technology. What displays do we use to provide these augmentations? Tracking. How accurately can we determine where the user's location is, and how accurately do we need to provide this information? And finally, we have human-computer interaction aspects in the sense of how can users actually interact with this virtual information to make it believable, to really make it natural to interact with it. And another aspect when we develop such experiences is variability. If you have a big desktop computer in your office and you have a very small space where you can put some wires, you can technically run a very high fidelity experience without any time limit. So you can put a user into this environment and they can stay in there for 24 hours a day, but they can move only in a very small range, and potentially you will have cables where they can get tangled, and maybe they will not like this experience at all. On the other hand, you can have some active devices that you put on a user, and with the new HMDs, you can ask them to wear this device, go into the world out there, and experience AR or VR on the go. The benefit, of course, is these are lighter, so users can actually wear them, and you can use them in a large area, but you have much less computational power compared to a desktop computer. And compared to the desktop computer, they will run out of power very, very quickly. So if you give somebody a HoloLens, I think it will die within 1.5 to 2 hours of use, and the whole experience will be over. And finally, you could utilize passive devices that, for example, activate only when the user is touching them. So by closing a short circuit, suddenly a button that has been pressed by the user can provide some information about the surroundings. These are lightweight and they can be used over a very large area. But when they're being used, they have a very short runtime and they are very sensitive to potential noise. Now, to provide this experience, it is usually visual information that we are focusing on. And here we have different types of displays. We have spatial AR, where we are projecting onto screens or onto objects. We have virtual reality head-mounted displays. We have video see-through experiences where we are using either displays or mobile devices, for example, your smartphone or your tablet PC. And finally, we also have optical see-through experiences, which can be again presented on displays or through stationary screens. And last but not least, we have also haptic, acoustic, thermal, and or olfactory experiences that we can address. And I will go into more detail on all of those over the next couple slides. Spatial AR, I think most of you are probably familiar with this from projection mapping onto buildings. If you have ever gone to Disney World, you will probably have seen this augmentation of the castle. And we can modify the appearance of objects and the user's experiences simply by projecting a lot of information onto existing objects. In the case of shader lamps at the bottom, we can modify, for example, the appearance of a model of an object with different textures. If you have a customer who wants to decide what color of a car he wants, well, you can simply project different colors, and then the user they can see it from different areas. They can see what they like, what they don't like about it. But we can also imagine that projectors are now very, very cheap, and we can all buy them. And there have been concepts that our whole office becomes a single projected area. So we are projecting onto different walls, different information. We can interact with this information, and we can therefore create a ubiquitous environment where we no longer distinguish between a computing area and the experience. And this kind of like projection on different areas has also been utilized in the past in virtual reality to create cave scenarios. The benefit of a cave is that we can easily create almost a 360-degree augmentation around the user by projecting on the floor, on the ceiling, and on all walls. It is also being still used in driver training. So if you want to evaluate how well if you want to study how people are driving in their cars, we cannot simply go onto the road and put them into dangerous situations. Instead, we can use a simulator with a cave environment around it, where we are projecting high quality graphics and create a very realistic experience. Now, you could potentially also scale up this whole concept. As you can see in the bottom, the allosphere in California. The whole sphere is the size of a building and has very high quality projections. I think it's 2K or 4K nowadays. Projectors onto all wall areas of this sphere. So you can create very high resolution graphics. And you can use this to explore human aspects or large data information. But of course, we cannot easily put all of this in our homes. And nowadays, we luckily have very cheap virtual reality displays that we can buy that provide high fidelity information. So the VR displays, they are simply a monitor right in front of the user's eyes. They have some information, some trackers to determine the user's position, the user's orientation, and render the graphics according to this information from the tracker. We have different, of course, devices. We have standalone systems, or we have also much cheaper devices where you literally put your phone into a cardboard and give it to the user. Now, when we want to develop AR, we cannot use a VR display as is because, well, it's clear it's cutting off the light from the real world. We cannot see anything beyond the display. So for a long time, what has been utilized were video see-through displays. You take a VR display and you put a camera onto it that is capturing the real world. And by showing the user the image captured by this camera, you can create an AR experience where the user is seeing the world in this VR display. The benefit is clear. They are very easy to build. You literally need just 2 cameras, as you can see on the top right, and you show this image on the display and you have done. You don't need to worry about transparency issues because you're simply overlaying the graphics on top of the image. You don't need to worry about calibration issues because you know exactly what you will be showing to the user. So it is very easy to build, but it suffers from several problems. First, the user is seeing what the cameras are seeing. The cameras may be at different locations from our eyes, different interpupillary distance, different positioning, maybe they are a little bit higher. They have a very fixed color perception, so we cannot capture the colors as we have as humans can. We cannot change the focus distance of the cameras. We have potentially low resolution, etc., etc. And despite these drawbacks, these displays have been used for a long time, and they are still actually being used. On the top left, you see the Varjo XR1. This is a new HMD that is promising the resolution and response rates at the same time as a human would have. Now, in recent years, with the advancement of technology, optical see-through HMDs have gained much, much more attention. The benefit of these displays over the video see-through displays is that there is no camera involved anymore. So we can see the real world directly. And through the optical combiners, what we do is we simply add the graphics into the light path, and the user can see both at the same time. Again, this technology has existed for a long time. I think the first HMD actually was an optical see-through HMD back in the 60s, but we have come a long way since then. Nevertheless, until a couple of years ago, what you see on the top left was a very commonly used optical see-through HMD. It was very bulky. You see very big optics. It has no tracking information, so you need very dedicated hardware and software to develop anything on these devices. And so only dedicated labs would use them. But since then, we have come to what you see on the top right, the HoloLens 2, which has a lot of sensors, which is providing a lot of information, making the whole experience very, very simple for the user. And also, but it's still relatively bulky. And on the top right, many of you may think that these are just glasses, but actually this is also an optical see-through HMD. They have designed very, very slim optics at the cost of a small field of view, but they have a very, very sleek form factor, and you can really wear them and just go out there, and many people will probably not notice that you're wearing something, some display. Now, at the bottom, you see a different variety of optical see-through displays. We were talking the whole time about head-mounted displays, but of course, you can also add the same kind of graphics to any type of mirror. So for example, on the right, you can put it into your car, which becomes a heads-up display. Or if you have, like on the left, a see-through OLED display, you can put it into a shopping window, and by tracking the users who are standing outside, you could be providing some augmentation of this shopping experience at the same time. Now, if you want to use any of these displays, what becomes important? Well, it is important to track where the user is and from where is the user seeing this. Here we see again the UNC walking experience on the left, which is a very small room, and you need to provide very, very quick and very high accuracy tracking. In fact, this experience is almost 20 years old, but still, even back then, by providing very high accuracy and very fast tracking of the user's head, the experience was so realistic that people would really feel like they are standing in front of a big hole and were afraid of taking the last step, even though they knew exactly that there is nothing there. So their immersion was very high. Their presence was very high in this environment. Despite knowing that they weren't somewhere else, they could not take this last step off the cliff. And now, but you can also expand the same thing to larger environments. If you are outdoors, maybe you need to localize where the user is to provide some augmentations. If, for example, here we are providing the augmentations of the edges of the building that the user is looking at. And commonly we are using two different techniques to do so. The first one are dedicated markers. Fiducial markers have been used for the better part of 20 years. And nowadays we have a lot of these kind of black and white markers on the top left that have been used in research. And more recently, we have these kind of image markers that you can see on the top right, where you have a very unique image that you cannot find normally in the environment. And by tracking this image, you can put the graphics directly on top of it or relative to it. And at the bottom, we see more commonly now becoming SLAM approaches. These approaches try to track features in the real world, and to understand how the user is moving through this environment. So I'm going to show you a small video. So here we can see that they are walking over through this convention center, and by tracking the location of the different features in consecutive frames, they are creating a unique, a common coordinate system, and they are tracking where is the user in this environment to make sure that the graphics will be presented at the correct location. Here, you can feed it here. And both of these approaches can be utilized for two types of tracking. The first one is inside-out tracking. Here, the sensors that are measuring the environment are on the user. For example, the HoloLens is an inside-out tracking system because all the sensors are on the user's head. And these sensors are tracking where is the environment relative to them. We could also do the same, not just with SLAM, but also with fiducial markers. We can place a lot of markers all around the building and then track the user as he is going through the different floors or the different rooms by detecting each of these markers. Again, the sensor in the user's head is detecting the marker, so it's inside-out tracking. Outside-in tracking is the inverse. We have some sensors in the environment looking at the user. These can be, for example, cameras, or these could be Wi-Fi routers that are detecting the location of the connected devices, or some other Bluetooth chips, again, that are detecting the devices that are connecting to them. And both of these can again be applied in different scales. And it is all a question about how accurate do you need to be? And this will determine what technology you will use. For example, on the top left, we see AR browser. These kind of browsers have existed for the better part of 10 years. They're simply overlaying some information about the world when you're looking at it. They can tell you, oh, there's the church over there, or this is where the university is. And you don't need very high quality positional information. It's simply sufficient to get the GPS location and maybe the orientation of the device to get a general idea what the user is looking at and what should we be augmenting. On the other hand, if you want to create a more high accuracy experience, like you see, we'll see in the bottom in the second, we need to really determine where is the user in this city, where is the user exactly looking, and what is their location, not maybe with the precision of a GPS, which is about 10 meters, but with a millimeter or centimeter accuracy. So as accurate as possible. And again, all of this comes down to what kind of experience you will be developing and what is the fidelity that you want to achieve. So here is an example I want to show of this experience. Has been specifically designed to use, it's using the HoloLens, but the goal is here to create an experience that is not just a room scale experience, but on a larger scale. And this work was done by Damien, who is also in the chat here, and is probably someone. So you can see that by combining a lot of information, this area, which is relatively a large scale, can be created, and the user can be localized in this area. Now, this is nice and well, but how would we scale this kind of system up to work on a city scale? So here, this was 90 by 180 meters, and it was working decently well. But the moment we go, let's say, from the block area to a city area, now we need still to localize everybody with millimeter and centimeter precision. There's still a lot of work that needs to be done to achieve this. And once we have localized the user, well, next comes the question about what kind of graphics do we want to show to the user? Do we want to show very, very high fidelity graphics like what is being done in Wellington? So they're developing computer approaches to create really realistic computer graphics, in this case for underwater. Or do we need to consider the what objects are in the environment? On the right, for example, we have been estimating the reflectance properties of different objects, because even if we render an object like you see here on the left, the location is correct of the object is correct, but it is not following the light properties of the world. So it doesn't have any specular reflections, or the light maybe is in a different location. And this is ruining the whole experience and the whole immersion of the user, because the user says, oh, this is clearly not from part of this environment. But if we start estimating the optical properties of the real world, trying to estimate where is the light coming from, what are there any specular objects in the world, we can ideally apply the same concept then to any augmented reality object to increase this experience that these virtual objects are part of the real world. They are behaving in a consistent manner with the real world. But we, at the same time, have to also consider the uncanny valley. Getting better and better graphics does not necessarily mean that the user's experience will become better and better. At the bottom, you see a study that was conducted by Volante and his colleagues, who wanted to see if users will respond differently to very realistic avatars, or sketch-based avatars, or maybe just, well, sort of okayish graphics. And what they found was actually that there was not necessarily an increase in the user's empathy towards the realistic avatar, because they were coming close to the uncanny valley. That means that people were starting to look for these kind of like small mistakes in the graphics, small mistakes in the whole experience, which would detract them from the experience itself and would actually ruin the whole belief that this is a real person that they are talking to. Now, so far we have been talking only about graphics, but there, as I mentioned before, there are also other senses that we could be addressing. On the top left, you can see a study that was done to modify a user's perception of taste by presenting a different smell. So what they did is they always gave the user the same cookie, but by providing different smells and different visual augmentation on top of this cookie, they could actually make the users believe that they are eating a chocolate cookie or a strawberry cookie or a peanut cookie. And in the middle on the top, you can see that we are looking at modifying the user's taste perception. So it's before we were modifying their smell. Now we modify through this mouthpiece with the electrodes by providing a different current. We are changing the taste of the drink that the user is drinking. So suddenly they may feel that they're drinking something sweet or something sour, even though the drink itself doesn't change. We can also change the haptic perception. So make the user believe that there is actually a virtual object here that they can touch, that they can pick up, that if they throw will hit them and it will hurt. And here we were using on the top right, you can see this haptic device, haptic arm that is hanging there. And this one. I thought this was a movie, sorry. This haptic device, and they had this rod attached to it. And with this rod, they could try hitting different objects on the table. And then they would feel really different weights and different haptic response and different movement of the virtual objects, thus increasing the whole realism of the experience. At the bottom left, you can see a different variation of this where they are applying different gimmicks to create the illusion that the user is walking upstairs. So this device under the foot can extend and can contract, creating the illusion that the user is walking up the stairs endlessly or walking up and down different surfaces, even though they are technically just walking on a flat surface. And of course, all of this is great if you apply it for the user's immersion and the user experience, but you could also create a very, very controversial systems. Here on the right, you can see the Kissinger. And this was actually a research project, and it is combining actually a lot of these augmentations into one device. It has video feedback from the users. The pads, you can see that they are kissing. They are providing haptic feedback with deformable surfaces. They also have some scent distributors in the device, so they can send out different smells. So they're creating a lot of augmentations of the user's senses, but I don't know if this application scenario is really something we should be aiming for. So I leave this up to your thoughts and discussions in your labs, maybe. Now, even if we create all of this, if we cannot interact with this virtual content, it is not very helpful. And here we face still also a number of challenges that others will be talking about throughout the course. We are so used to using a keyboard and a mouse in our desktop environment, or let's say a mobile device. Now we go from this 2D experience to a full immersive 3D experience like we have in our real world. How should we interact with this content? Should we use some dedicated devices that the users need to carry around? How do we interact with objects that are close, that are maybe further away? Do we need to stick to the physics of the real world? Or should we actually utilize that the user is interacting with virtual content to bend the rules, to allow the user to pick up an object that is 2 kilometers away, to zoom in and to teleport to a new location. So how should we interact with this? And there, of course, you could also say that there are other problems as well. If we are talking about optical see-through AR or video see-through AR, so AR in general, we have the problem of occlusions. Should we should the graphics occlude the user's hands, or should the user's hands be semi-transparent or correctly occlude the virtual object? Ideally, this would be the case for something that is very close to the user, where we can provide haptic feedback so that we can give a natural way of interacting with virtual objects. But if something is very far away, this whole principle becomes maybe no longer valid, because we can no longer grasp this virtual object that is far away. We want maybe to have some other visualization. And there are also many, many different things that have been explored, and this should appear a little bit later. But one of them, as I said before, would be gestures. So similar to if you have seen Minority Report, we could use different gestures on surfaces or in the air and interact with the virtual content. And the Microsoft HoloLens had these two very unique gestures that would create different menus. The bloom gesture would open a menu, and the click gesture would be used for selection. Every user I gave the HoloLens to always understood the bloom gesture. It's very easy. 99% of them did not get the click gesture. You would usually tell, do it like this, and then they try and they click, and it never works the way it is supposed to be. So learnability of gestures is another big question that we need to consider when we are designing them. Now, you could also say, well, let's give the users peripheral objects, like, well, everybody has a smartphone. Now they can use their smartphone to interact with the virtual content. Or we have the joysticks that are very cool, and now users can very nicely use them in virtual reality to point at different locations to select them, to bring the joystick as part of their hands to select an object, to create. These are very, very nice devices, and they're working very well. But can we use them in more crowded areas? Well, we can use them at home, but imagine you are sitting in the subway, and now you're taking out your controllers and you start hitting all the people around you. So clearly, gestures and controllers are not a very good option to interact with virtual content in these kind of like crowded and more social environments. So what kind of gestures, what kind of interaction paradigms should we be using there? And in recent years, there has been a lot of work on the on-device interfaces. So for example, here we can modify, the user can interact with the virtual content simply by sliding the fingers on the HMD by interacting with the touchpad that is attached to the other side of the screen. And the whole goal here is to get rid of the need for peripheral devices and to allow the user to still control and interact with this virtual content. Or we could use as well eye gaze tracking to allow users to point at different objects that they're interested in and simply select them by looking over there. And there are many, many other ways we could be utilizing this information. We could be interacting. What I wanted to show here is that it is still a very active research area. And I think we will be talking about this in the coming lectures as well. So come again and please pay attention there. So with this, I'll just very quickly show all the papers that I have referenced in here if you are interested in checking up on some of the definitions. And thank you very much for listening, and any questions.